Do you need a microphone?
How are you? How do you like the pizza?
No, I like the pizza.
Okay.
Because it's not healthy.
I think you can. I'm super hungry. I haven't.
I think it's okay.
I'm like, I've already. Yeah. I know. I'm such a snake, I'm so big, so happy. Not being allergic to anything. This is amazing, isn't it? You can actually eat anything when we thinking every time, oh my god, what is that? It's like,
Why are people so sensitive? I mean, I'm not blaming them. I'm just saying,
well, if you think about it, first of all, sometimes, yes, following.
Hi everyone. How's the pizza? It's good, okay?
Yeah.
Yeah. Did you have too much ham and apple? Pineapple? If that's my choice, I ordered 4 for myself. So hope you like it. So thanks for coming again. So how many of you is the first time here? Is it first comer? Okay. Oh, okay. Okay. So you don't know much about this meetup then. So I wanted to tell you about this meetup and the company called H2O.ai. And then I will give the talk stage to the first speaker, SK Wellington. And then we have a break, and then we have the second talk, and then we have more time for beer. Okay. So how many of you work in AI, machine learning, data scientists? Are you data scientists? Yeah. Have you seen this before? so I do work for a company called H2O.ai. Believe it or not, it does work for fundraising. So we had the last round, we had round C funding last year, led by NVIDIA, Wells Fargo, and then we are actually a software company based in California. So we create different machine learning platforms. So one of them is also called H2O, the open source H2O, and we have the commercial one called Jarvis AI. So, but today I'm not going to talk about this product. I'm going to share a stage with other speakers. So I want to make this more diverse for other people to join this meetup. So the team is mainly in California. Today I have Ian there with me and Kiba there next to me. So we are usually have this office in California, but in UK, in London, that's my home. So I don't have the office to host you guys. So thank you for coming back to give us this space. So really, really appreciate that. Just one more slide for marketing. So this is us on this magic quadrant. So what does that mean? So this is based on the customer feedback and the features of the software. So every year, Gartner, they look at different big companies in this space, or data science and machine learning space, and they look at people with companies with different customer feedback, different software features, and put them into different quadrants. So you can see H2O.ai is here, but then we are really small. We only have about 120 people comparing to the other big guy. So we have one of the leaders with the most completeness of regions. It means we're quite future-proof. That's it. That's for marketing. And this is mainly my job here, so I try to organize different events in Europe. And this is the biggest one I have in London, so we have about 7,000 people now. And that's my life for the last 2.5 years. So I travel around different places in Europe and US. So every time I go to new places, I'll try to take a photo of that place, or either myself, a selfie, or some of the landmark in different cities. So last week I tried to summarize what I've been doing for the last 2.5 years. So I don't think I'm like a data scientist anymore. I'm more like a photographer or traveling data scientist. So I've been to quite a few cities, in Europe, US, and I may go to a few more in Asia, in the coming months. So this is the time I need to ask my team to be ready, because I need to do a survey with my team. Where's Ian? He's there. So usually I need to ask the question. So GDPR, I need to have your consent. Is that okay? Yeah. If not, you can just duck. Okay? It's super easy. Do you want to come?
never done
Okay,
this,
so-
Joe. My first
It's our first selfie with Joe.
It's over for this. Hiatus.
Wow, this is ambitious.
And we smile. You can wave in the background, okay? Let's go. Thank you. Thank you.
That's a cool tool.
Yeah, and that's my job. But, yeah, it's really hard to do up. Yeah, so bear with me. Okay, so just a bit more about this meetup. So I'm really lucky to have different friends and different data science group in London helping me out before I have this group. So this is the first time I created a group. So it's back in February last year. It was only about 300 people joined the group. So it's mainly for me to talk about H2O. So hard selling, H2O at the meetup. So then we have to hide AI, machine learning, travel around in Europe, US, and somehow by the time I checked it last night, we have about 7,000 members. So thank you for joining us. Thank you for being a part of this community. So really appreciate this. And I'm not only saying this to thank you. I'm also going to give back to the community. So we support other groups here. So Women in Cargo, Alice London, other groups in London as well. We try to give back some pizza, just something small enough to help them going. So just if you want to go to one event this Friday, so we have a booth at this event called the Tech Day London. So it's mostly a free event. So if you have this code here at the end free, then you can get a free pass and get into this. I think it's mainly like exhibitions more than a conference. So you have many people talking about their products. So feel free to go there for 2 hours. I'll be there from 9 to 5 if you want to look at H2O platform. So you can come to a booth. I think it's 102 as the number of the booth. And the other events I want to mention is our own conference. Finally is going to come to London because we used to do this in US, either in New York or San Francisco or Mountain View. But this time we have this in London, so it's very close to you. So how many of you have the ticket for this event already?
You're out of free tickets.
Okay, cool. So just let me show you. So on the first day we have the workshop, so you can, if you want to try some of our software with hands-on workshop with a team next to you showing you how to do it. We have the first, in the morning we have the Java's AI workshop. And then in the afternoon we have other open source tools like H2O Free, open source H2O, and Sparkling Water, which you can use H2O open source with Spark. And we also, on the second day, which is the main conference day, we have more use case, so you can come and listen to how other customers or our users, how they use H2O for their business. And there's also a really cool Cargo Grandmaster panel. So we have 7 of the Cargo Grandmasters. There's only about 100 of them in the world, so we have 7 of them coming to London to talk about their experience in cargo and data science stuff. So that's very cool. So that's all from me. So I want to give the stage to Helen back. So if you want to give instructions first, thank you.
Hi everyone, thank you for coming tonight. I am Fanny, I'm part of the recruitment team at Quantum Black. I will not give you a recruitment talk tonight because this is not the aim of the evening. I just wanted to give you a quick introduction about Quantum Black and where the company started and what we are doing today. Thank you very much for organizing the meetup. We are very excited and very happy to host such meetup and to welcome you all. So just to start with, give you a quick introduction. Quantum Black was founded about 10 years ago now, historically by a data scientist, a software engineer, and a former McKinsey consultant who was looking after business development, marketing. And the fun fact is they started in Formula One, which I personally think is quite cool. So they did quite a lot of projects improving either the car's performance or the positioning, tracking the data and making sure that they could use the insights to just go the extra mile and improve the performance of the teams. It was really successful, and this led to the acquisition of Quantum Black by McKinsey 3 years ago. Since then, it's been a great success. We have been growing massively from both McKinsey and Quantum Black sides. We are now opening another office, maybe early December, so more information to come, and another one early next year as well. So we are now about 300 people, just all over the world. So we have the main office here in London. We have offices in the US, in Brazil, India, Sydney, and very soon one in Canada and another one in Asia. So it's a very exciting time for us. And if you're wondering what does Quantum Black do, to give you a bit more information, so we are a consulting company. We focus mainly on the tech space, and what this means is that we provide end-to-end services to our clients from very early stages when we try to understand what are the type of problems that they are facing and what we can actually do to help them, until the very end of our engagements when we deliver a fully built and implemented product. So it's not just about understanding the data and finding some insights, giving them information. It's actually taking these models that are built by a consultant into production and then hand over a product that is fully managed by our clients. So it's very, very exciting. We are growing massively, and we are now at a point where we are also really developing our internal assets. So we have multidisciplinary teams from data engineers, data scientists, machine learning engineers, software engineers, designers as well. This is something we're very proud of, to make sure that it's not just about making the product work, it's also making sure it looks great and can be, very easily adopted and reused by the clients. And now more focusing as well on the internal asset that we are developing, recruiting again mainly in this area. But this is not about Quantum Black tonight. I really hope you will enjoy the talks. Thank you again for you guys. I hope that you will enjoy the talk that will be done by Manisha, who is one of our data scientists. And if you have any question, you can either find me or Mariana, who is at the end of the room here. And if you want to know more about Quantum Black, we will be at the Silicon Milk Roundabout in November. So feel free to just come and see us. Thank you.
Let me now pass the stage to SK. Yes. Okay, just take the lights up. You want get it first, but I can put my password, make sure it. Okay, so the stage is yours.
Thanks. Hello everyone, thank you for coming on a Tuesday evening. For the next 35-40 minutes, I'm going to talk about image processing, especially using point clouds. And obviously, I think trying to cover such a massive topic in 45 minutes is going to be so difficult. I have a bunch of slides, and I'll not be able to cover all the slides. But the objective of today's presentation will be just to introduce all of you guys to the topic of image processing, especially the point clouds. Image processing, among all of the topics within AI, has really picked up in the last 4 or 5 years. 2012 was the first time CNNs were introduced in image processing, and there's a tremendous improvement in the accuracy of the model. Actually, the top 5 error rate of the models, which was I think 25%, I think came down to 16%, I think 2012. So 2010, so 28 and 25% came down to 16%. And then 2015, within 3 years, the top 5 error rates of the models actually dropped down to 3.6%. In other words, every 100 images you give the model, blurry, occluded, non-visible, partial images of animals, model can easily pick and then identify what object it's looking at. So every 100 you give, they only make mistake in around 3 or 4. You know what the human accuracy rates are if you give the same 100 to a human being? Take a guess.
3 or 4.
3 or 4, actually 5 and 6, so around 6%. So models have become extremely accurate even in 2015. 2016, the top 5 accuracy, top 5 error rate dropped to 3%, and 2017, it's 2.6%. So if you have any of your funny pictures you want to send to your friends, be careful, there may be a model which actually can figure out what pictures you're sending. Anyway, whenever I tell that story, people normally laugh, but it's okay on a Tuesday evening. But all of these models are 2D images. but the world around you is not 2D, it's actually 3D. And more amount of research has been focusing on using 3D images and making sense out of it. So 2017, 16 we can say started the processing of 3D images, but 17 and 18 is when really the accuracy of the models are going up. So we all are living in that world where a new technology to process 3D images is really taking off. Maybe in a couple of years from now, or maybe 5-6 years from now, or when you all get married and have kids and whatever, then the kids will say, what? You lived in the time where you don't have models which actually can figure out 3D models? But that's what is happening. Where do you use the 3D models? Predominantly in healthcare, in gaming, the AR and VR situations, and of course also the autonomous driving, could be including your vehicles, or drones and satellites and all of that stuff. And I'm going to talk about a few models today. I will introduce historically what has happened, but I will focus on one model which has revolutionized the entire point cloud processing, and then I'll show a bunch of other models too. You know, a long time ago when I was about to make a presentation, I asked an expert, what's the best way of making a nice presentation? He said, make sure your slides are sparse. You don't have too much of information on each slide. But I just forgot that for this presentation. There are different types of 3D representations of data. You actually have descriptors which actually just describe the various elements of the 3D images. You have projections. If you have a 3D image, you can project that onto a 2D space and then run a model. Why would you do that? Well, I'll answer the question in a minute, but you also have RGB depth. So RGB, 2 dimensions, and then depth could be the third dimension, which is actually not called a full dimension. So it's called, you know, AI scientists like us, we're all weird people. So it's called 2.5 dimensions. I don't even understand what the half dimension is, but RGBD is actually a 2.5 dimension models of 3D images, and you can actually run CNN models on that. Volumetric data representation is, let's say you have an object. I can show something, but let's say this is actually a volumetric object. Even if the inside is empty, for the sake of processing the model, you tell the model that it's actually completely full inside. So you actually are creating a volumetric object out of a hollow object, and the model tries to make sense out of it. And there are two types of volumetric. It's called voxels, it's called voxelization. So if you take an image using your regular camera, you tell the model, oh, there's something inside too. So it's really one full object. That's called voxelization. Octree is, how many of you are mathematicians? Okay, I'm going to ask you an interesting question for all of you guys, which you tell me the answer maybe later, but this will be a good question for all of the mathematicians and all of the other guys who were scared of raising your hands. Here's a question. I'll come back to the image processing in a minute. Let's say you go to a store, you buy a pencil for £5. You have a 20-pound note. You give it to the storekeeper 20. You get a pencil for 5, and he doesn't have change for 15 pounds to give it back to you. So the storekeeper 1 goes to storekeeper 2 to get 4 5s, and then comes back and gives you 3 5s, and with a pencil you go home. Okay? After some time, storekeeper 2 comes back to storekeeper 1 and said, you know what, this 20 note is a fake one. So storekeeper 1 says, oops, sorry, and then he gives a right one. Off goes storekeeper 2. How much storekeeper 1 lost in that transaction? How much he lost? How much did he lose in that transaction? That's a question for mathematics, but I'm going to come back to that image processing. And if you know the answer, tell me during the break. I'll tell Ian, he's going to give you a prize. No, he's going to just thank you for the answer. Octree is a recursive data structure that breaks down an image into pieces of 8 and keep on doing it until it becomes the smallest piece. So you have an image of, let's say in this case, a rabbit, and you break it down into 8 pieces, and each of the pieces becomes further 8, and then once you reach a certain level, you actually can make it a 2D image and start processing it. One of the more famous Euclidean data structures in 3D representations is multiview. When you have a 3D image, because the AI engineers, AI scientists were very comfortable with CNNs, which actually work on 2D, the effort or the attempt was all the time convert a 3D into 2D and then run CNNs, because CNNs actually can run really well on 2Ds. So multiview is nothing else but if you have an image, let's say there's a chair here. You take 8 or 10 different pictures of the same chair from multiple angles, multiple views. It's the same chair, but every time it's a different chair for the picture. And then you run a CNN model on all of those 8 or 10, and the model will tell you, a model will learn that's a chair, and eventually when you have a 2D image, you can convert that into a 2D representations and run the model. All of these are Euclidean data structures. You know what a Euclidean data structure is, or a data space is? When you have 2 different points in a space, you actually can measure. The distance metric is easy to measure. The non-Euclidean is sometimes it's not very easy to measure those, especially point clouds, graphs, and meshes. I won't take too much time. This is a funny thing. All I mentioned AI scientists are little weird guys. We are still struggling to define whether point clouds are actually Euclidean or non-Euclidean. You know, I just picked up this from a paper, so I didn't want to hurt the sentiments of the authors. I just put it in the non-Euclidean, but I personally believe point clouds are Euclidean. But if you want to wrestle with me, we can talk later. Point clouds are nothing else but a set of irregular points that reflect the image you want to take. My company actually, we designed a lot of Lighthouse. If you look at this room here with multiple chairs on the ceiling and the walls, it's relatively plain, simple image. Go to a factory, go to Google and find out, search for images of a factory. You'll find thousands of pipes and pumps and walls and knobs and so many things. And if you take an image of that, it's really, really complicated image. The LiDAR we have, it's called BLK360, it takes less than 2 minutes to take an image. It has almost half a terabyte size, one image, and 200 million points. Could be anywhere from 100 to 200 million points. It takes in less than 2 minutes. And if you really want to create a digital twin of a factory, you actually take multiple images, point clouds, and then stitch it together, run a model, and then model will figure out what is where. To make a simple example, if you take a 3D point cloud image of the street outside, you can take multiple images and stitch it together, and then you can assume you're flying through the space, and you can actually see the doors and the windows and the trees and the people and the cars flying by next to you when you're walking around, and the images are changing all the time because you're walking through a point cloud. Meshes are nothing else but a bunch of polygons, many times could be triangles, but these are all 3D representation of data of images. I'll skip this. One of the earliest model, actually I have 2 models which are earliest, 2016, 2017, where the objective was, how do I translate a 3D image into a 2D structure? I mentioned to you, I defined to you earlier Octrees or Octree data structures. This model 2017 and also the next one, or both of them use the Octree structure. By the way, the paper I picked up, I'm going to show all the various papers published in the last couple of years, 2017 and 18. One of the reasons I put the link is, of course, to let you guys do further research. Another is also at a 7 p.m. on a Tuesday evening, sitting in a nice chair, having a beer. I think maybe once in a while, tempting to fall off to sleep. So maybe you can open your cell phone and take a picture once in a while on the screen. So it'll also make you do some physical activity. That's the reason why there's a link here. I may share the slides later on, but if you guys want to. If you look at the solution here, you take an object, in this case an airplane, you have an object and you break it down into pieces of 8 recursively, an octree, and then after that, each of the pieces can be just a 2-dimensional image or a piece of the image, and you can just stack it on top. Now it becomes just a regular 2D image processing problem statement. If you have heard of how those things, those apply, you have a regular color image, RGB, you can actually have, that means 3 channels. you run multiple kernels on each of the channel, and you actually have a feature space. And depending on the number of channels you run, let's say 64 or 128 channels, you actually have 128 layers of feature spaces in the next level, and then you do another set of kernels and keep on doing it, whatever your GPU power allows you to, 5 layers, 10 layers, 15 layers, 50 kernels, 100 kernels, or 200 kernels, and then at the end of it, you actually have a classification or segmentation, whatever. Same logic here. So if you are comfortable with 2D image processing, this paper and the next paper are very, very similar, where they convert a 3D image into a 2D image. But this is not the exciting part. Research actually moved. PointNet is the most exciting model that has been proposed in the last year and a half. Of course, the authors have further improved this paper to PointNet++. The AI engineers are not very creative in naming it, so PointNet and PointNet++ is not great of it, but I don't know why they couldn't give a different name, but PointNet is the most interesting model in the sense, for the first time, the model can take a raw point cloud input as is, no pre-processing required. Also, point clouds, I don't know if you guys know that, point clouds are canonical. You can translate or you can convert any other 3-dimensional image into point clouds and vice versa. And the biggest problem of point clouds is the data is irregular. The points are irregular. You just can't find points all the place. A 2D image is a regular image, or the pixels are very regular. What does that mean? If you look into a 2D image of 224 by 224, every pixel has a value. Even if that pixel represents the background, or space, or just the sky, every pixel has a value, and you actually take the pixel for your processing. But in 3D, sometimes there's no space. There's just no point, just an empty space. So they're irregular. Running a point cloud through the regular CNN does not work. So here's what they did, which is very interesting. They took the hypothesis that if you use a symmetric function on an irregular data set, the model would be able to figure out even if those points are perturbed. Now, what is a symmetric function? Again, there are only 4 or 5 mathematicians. I'm guessing some of you guys did mathematics even on your 10th grade and 12th grade too? Yeah? Yes? Normally, yes is this and no is this. Okay. A symmetric function is if you have a series of actions you do on some numbers in any order, the outcome should remain the same. For example, addition is a symmetric function. 2 plus 3 is same as 3 plus 2. Multiplication is a symmetric function. 3 times 2 is 2 times 3 same. In the CNN context, max pooling is a symmetric function. Average pooling is another symmetric function. Weighted average pooling is another symmetric function too. They tried all of these symmetric functions and they found max pooling gave the best results. So actually they do a max pooling of all the points after putting them through some transformation. That is the fundamental logic in this entire paper. So you take the points, n by 3, n is the number of points, and 3 is the dimensions. You can take more than 3 dimensions. For example, in a point cloud, every point has at least 3 dimensions. What are they? X, Y, Z. You can also add additional dimensions, like, for example, the brightness of the color, or maybe something else you want to add. That's fine. But let's say you only take 3 dimensions, like a grayscale image, point cloud. You see the n by 3, which is just one massive matrix of 3 dimensions pointers, and do an input transformation. Ignore for a minute what the input transformation, I'll explain that to you. And then after transformed, you put it through a regular MLP, multi-layer perceptron, almost like an RNN, with a bunch of activation functions, bunch of redos, bunch of normalizations, that stuff. Just a simple. And do another transformation, and in both the case, transformation is nothing else but running a 1 by 1 or 3 by 3 kernels on it, just for reducing the dimensionality and bringing it back to the original dimensionality. For additional information, you can read the paper, but the point is, take just the raw points, 3 dimensions of each point, run it through some transformation, and then put it through your NLP, MLP, sorry, multilayer perceptron, and at the end of it, you actually get 1024 dimensions for each point, and then do a max pooling to get one single dimension. In other words, the entire point cloud is converted to a single vector, and that is the global feature of the point cloud. For example, if you take an image of this, you end up having a 1024 dimension vector that represents this object, and similarly other objects. And then you run the scores on this using a couple of other MLP layers, and then you actually get, using a softmax, you actually do a classification of the objects. Very, very simple approach for the first time using the raw point clouds. Got fantastic results in the sense even some of the earlier models where they were doing handcrafting of features, this model, without any handcrafting of initial features or presentation, learned the classification and got better results. So actually, you have the multiview CNNs and you actually have 3D shape nets and some of the earlier nets. This model actually surpassed many on many fronts. But that's only the global feature, which is if you want to do a classification for the entire object. But in the real world, in any point cloud, you will not find only one object. You actually have multiple objects. Yes? And to do the semantic segmentation to identify multiple objects or even multiple instances of the same object, they use the global feature concatenated with the original dimension of individual point, where in this case it became 64 dimensions because you put it through some transformation. As I mentioned earlier, you will figure out how to do the transformation from 3 dimensions to 64 dimensions, concatenate this each point with the global feature, and now this means every point in the point cloud is also aware of the global features, and you can do a semantic segmentation. What happens after that? Then let's say if you have only one object like a chair with the background, that is 2 classes. You have background and then you have chair. Do you guys know what semantic segmentation is? It's pixel level classification. Like in one object, if you say there is a chair, in semantic segmentation, you will find every pixel in point cloud context, every point will be assigned a class. Does this belong to a chair or not? And if there are only 2 classes like background and chair, then it will pick all the 100 million points or all the 200 million points and pick the class. And it does the color coding. So in an image which is processed through the model, it will give one color for the entire background and one color for the chair. So you can clearly see the chair. So because the global feature is being added to every point, the model is able to understand the chair, which includes the armrests, the back support, the seat, and the legs, and then separates that with the rest of the background information. This made a tremendous impact in point cloud world and image processing. They actually, I think, open source the code too, just in case if you want to play with it. That's paper. And then they came out with, I'm going to skip this, I'm going to go to PointNet++. The one weakness in point cloud model was, even though it's picking up the global features, sometimes it was not very strong in local features. When I say global versus local features, imagine, again, that single chair. I don't know if you guys can see a chair. Here is a chair, but you guys are all sitting in chairs. If you look at the chair, model was missing sometimes the legs of the chair. Especially, let's say if you have 2 chairs very close to each other, the legs are really touching. Sometimes they just can't find out, the model could not figure out where the edge of the first leg is and where the edge of the second leg is. So that local features, in a grand scheme of things, model was missing. And that was only just if it's 1 or 2 chairs. But if you have a complex image scene, let's say you have an autonomous car and then you have a lidar sitting on your car and the car is going at the speed of, I live in Silicon Valley, we use miles, but let's say in UK, we'll talk about kilometers per hour. I don't know, what's the speed limit you guys drive? Is miles still? Oh, fantastic. What's the speed limit you guys have here? 60? 70? 70 miles per hour. If you have a lidar sitting on your car and driving at the speed of say 70 miles per hour, and the response rate, of course, is less than, let's say, a millisecond or a couple of milliseconds, I think you would have already crashed into a car or another pedestrian or a tree before the model says, oh, hang on, there is a pedestrian coming up. But semantic segmentation, you got to really be the model has to be fine-tuned. If there are a couple of cars going in front of you, or let's say a couple of pedestrians walking in front of you, and the model cannot figure out they're two or one, then the model can give a wrong suggestion to the car, and the car can do something wrong, damaging for the people. So they found that local features were not really being picked up by PointNet. So PointNet++ actually, they said to pick up the local features of a complex scene, let's do the following. That is, run PointNet as a model recursively for every few points. So if you have 200 million points, or let's say 100 million points, pick maybe 1,000 or 10,000, maybe 100,000, and run a PointNet on it, and the so-called global feature in this context becomes a local feature because you're actually focusing on a small piece of the overall image. So now, just the leg of the chair is a global feature because you're only focusing on that part. So the model actually, you run the recursively, so you pick a few points, and then start running the pointed model, and it just picks up and then start. It was computationally expensive, but it really improved in terms of the accuracy, and in terms of the semantic segmentation actually picked up very much, which is what every 3D image processing model is supposed to do, because the semantic segmentation is used for, as I mentioned earlier, AR and VR and autonomous vehicles and stuff. I have a couple of other models which I'm going to talk about. How much time do I have? Another 20 minutes maybe. Well, by the way, do you guys know that they have locked the doors? You can't leave till my presentation is over. No, I think it's not true. Yeah. Sparse lattice network, SPLATNet, was a model that was published in 2018. The paper actually came in Feb of 2018, just a few months ago. Here is almost the same version, like try to use some of the 2D model processing. Here they introduced a concept called BCL, bilateral convolutional layer, which is nothing else but you create a splat. So pick a few points which are irregular, throw a mesh on it, a mesh shaped object on it. Like for example, like this. So when you do that, you see some of the points fall randomly somewhere, sometime on the line, somewhere close to the edge, different vertices, or somewhere in the middle. But for every point, once you do this, for every point you have, assign the relative weights of each of the point to the 3 nearest vertices. In other words, if this point has a value x1, and if this is right in the middle, this point will get x1 divided by 3, x1 divided by 3, and x1 divided by 3. And for these points, let's say this is y1, and this contribution is y1 divided by 2. So this point will become x1 divided by 3 plus y1 divided by 2. You keep on assigning points to the vertices. What are you trying to do? You're trying to create a regular structure from an irregular structure. Now, this irregular points, which are in yellow here on the gray mesh, will look like a very regular structure. You see all the black circles here. And after that, you just run a regular kernel. But the kernel is going to be not like a regular square looking or a rectangular looking. You know what the term kernel is? Or a filter is? So if you have a typical square shaped or a rectangular shaped filters, you actually have a splat, the same lattice shaped kernels which actually can convolve on it and then figure out what it is. So again, it seems to be the approach of many AI scientists for image processing to use some of the 2D image processing models, because between 2012 and 2015, the 2D image processing models have become so stable, so intelligent to figure out what the image is. They're trying to use similar techniques. So this actually model really fared well. I don't have the results I don't have it in the slide here, but if you want to pick, you can look at the slide into the paper to find out about how the model did in terms of semantic segmentation. Multiresolution Network is another model. I want to explain if you can understand how typical convolutions happen. This is the first time of all the models they have used encoder and decoder. You had a question?
Yeah, and I was just wondering how the previous model was performing compared to PointNet++. This one?
That's what I mentioned. I don't remember right now, but I think this and this model and PointNet++ might have been almost the same time, so I don't know the results. But you can check the paper and then you can figure out. I don't know the answer. Paper should be having the relative information. For the first time in this network, they have used the encoder and decoder concept. I don't know if you have done any NLP, natural language processing models. You actually have encoders and decoders with the sequence models. This was very interesting. I have not seen any other paper which actually has used encoder and decoder, but look at the results they actually have. They beat even PointNet and PointNet++, even MRTNet, KDNet, which I didn't explain, which was my. They beat the PointNet, PointNet++, KDNet, MVCN, Multiview CNNs, Multiview CNN with multi-resolutions, Octrees and ONet, which both of them I showed in the very first two slides. So it's really doing a fantastic job. And also they used a little bit of a transfer learning using VGG11. There are a few other models. What I'm going to do is I'm going to talk for another 5 minutes, maybe 5 minutes, and then I'll open up for questions and if you have any questions. There are a few other models like squeeze-seg. Actually, squeeze-seg came from the earlier model called squeeze-net, which is a 2D model. And for the first time I've rarely seen conditional random field CRF being applied for semantic segmentation in this model. Which is again, you see the convolutions happening and you see the deconvolutions happening, and then you also have the skip connections where you let the layer here not only get the inputs from the previous layers, but also directly get the inputs from a corresponding layer, which also made the model remember more of the details. PointSeg is a similar one. Again, this model actually did a fantastic job. If you look into the class like car, pedestrian, cyclist, but even some of the results. But the same, you have the convolutions happening and you have the deconvolutions happening and you have the skip connections. There was another model which published this September 2018. Which month are we in? October, yeah. LMNet is another model. Let me quickly jump to, Spherical CNN came again in May of 2018. That's an interesting concept. I mentioned the 2D CNNs where you have a square shape or a rectangular shape kernels which actually convolve. This author said, can we just use the same logic, but instead of doing a 2D filters, can you do 3D filters? But can we also make the 3D filters look a little more odd? So they actually picked a spherical looking 3D filters to apply on this 3D image. That's the only difference. Of course, they have a little bit of other structural and architectural differences, but that was a very interesting concept they used. Instead of using a 3D, but they used a 2D, they used a 3D kernels, but the 3D kernel also is a shape of a sphere. They still have good results. So I picked up all the models which are actually improving in terms of the semantic segmentation accuracy levels. All of them have their own positives and negatives in terms of computing power and stuff. For additional information, you can read the papers, or you can also send me an email. Okay. One of the worst scenarios in AI is the lack of data sets. And thankfully, in 3D image processing, there are some data sets available. There are a bunch of data sets available. Some of them are good, some of them are not so good. Some of the most common ones are ShapeNet and ModelNet. ModelNet actually comes in 10 classes and 40 classes. Kitty is another very popular one. It's one of the earliest 3D models, like CFAR. If you have been using 2D image processing models, CFAR is one of the earliest ones, and ImageNet is another earliest one, but they have other data sets now. But Kitty is similarly 3D, one of the earliest ones, but these two are more popular ones. But you have other stuff too. For example, you have pure synthetic data sets too. And then if you go to this website, you also find some of the leaderboards of which models are performing well on these data sets. And this, I've shown this picture only to tell you guys, if you want to really play around with 3-point clouds, there are data sets available. And YOLO, have you heard of YOLO? You only live once, yeah, not the other one you thought. So similar to YOLO 2D, you also have YOLO 3D. And even though this is not showing as much promise yet, but I'm sure people are going to work on it and then improve it. But if you look into the architecture, it's almost very similar to what the 2D, YOLO 2D is. Some of the research of late is similar to the 2D processing. If you have just the classification or localization detection, or also semantic segmentation. In 2D now, you actually are detecting the action flow. Let's say you have a video in a smart city type of a use case. You have a surveillance camera watching what's happening in the traffic, and the model sitting on the surveillance camera should only come into action if there's a traffic accident or a crime going on. Till then, it should not just do anything. So the model has to figure out the action flow. And similarly here in 3D point clouds, people are trying to figure out action flow, which is very useful for autonomous cars. It's a complex architecture here, but if you want to read the paper, that's a very interesting paper. Not much of research has happened in point cloud on action flow. And if you want to develop any of these models, and if you want libraries like TensorFlow stuff, there is 2 types of libraries available called point cloud library. They have a lot of modules available. You can play with it. And there's another library which is coming up and may not be the most exciting one, but you can try with that too. It's called Cilantro. It's the most exciting slides.
Thank you.
I'll be happy to take any questions.
You mentioned about Octrees, and there was a comparison between voxels. So when would Octrees be used most often?
Voxels was initially used because they just want to only look at the surface part of it, but if you just tell the model that it's a full object, it can figure out. Voxels was computationally very, very expensive because now you're filling up information which is not even there because you have more and more points you're filling up and the model actually tries to find it. So voxels are not used anymore. Octrees are being used earlier in 2016 and 2017, but Octrees also, you don't know when to stop the recursive data structure. And that's the first point. Second point is, you want to reach a stage where you don't want to pre-process the data before you even start using the model. Octrees and voxels and voxelization all was pre-processing the data, which was an extra computing cost. And after PointNet came, when it proved that you can have a good accuracy for a model where you just use a raw input, people just start working on it. So you don't see any more research happening in voxels and octnets. But here is a funny thing about AI. People publish papers only on successful ideas. I want to encourage people to publish papers on even failure ideas too. Why? Because when I want to do more experiments, I want to find out if that idea is already a failed idea, I won't end up repeating it. But no one wants to publish. Yeah, all AI scientists, we don't want to show how stupid we are, so we want to talk about how wonderful we are. And so that's a big problem. So maybe there is a wonderful opportunity to use just voxelization or even Octrees, but there's not enough papers because once people found out PointNet can actually do the raw processing, there's not much research. I've not seen enough papers for that. Yeah.
So when we talk about computation-intensive, models that require a lot of resources, on self-driving cars we require real-time processing, right? So resources are limited, of course. So how much resources are we talking about? How many GPUs are we talking about? Because
I live in Silicon Valley. I see many times the Google cars actually running around on the streets. I don't know if you actually have seen any such cars here in London, but we see. And like a kid in the fish market or in a zoo where you want to poke the animal because it's right there. I was driving and once in a while I want to mess with the car, just go into the car's lane. I don't want to see how the model responds. So right now, Google Car only runs at 25 miles per hour speed. Even the slowest speed is only 35 miles per hour in the inner city, but it only goes 25 miles. So I think the LiDARs, even though it's picking up really fast, the processing time taking so much time to really respond to what's happening. So I don't think models can really go for 70 miles. Tesla has even I think Volvo I've heard, but Tesla actually has a working model on the streets, but for legality purposes or whatever reasons, they say the driver has to hold the steering wheel even today. If it's an autonomous car, I don't see the purpose of even having a steering wheel, but I would rather want the steering wheel to be taken away. But so the computing cost, we recently acquired a company called Autonomous Stuff where we equip a non-autonomous car to an autonomous car, and it takes, I think, 5 or 10 GPUs that sit in the boot, whatever you call it in the back, and then we have an extra battery, and we have a bunch of sensors going all the way around. So I think in our company, or even companies like Google and Baidu and some of these companies trying to do autonomous cars, the models are constantly changing. I remember 6 months ago, 1 year ago, the model was detecting where the lanes was, and then deciding to whether change the lane or not. But now the models are focusing on how do I have an integrated approach of driving safely from point A to point B. Without then the lanes and lane changing all are going to be done. But to answer your question very, very specifically, I think there are a few GPUs sitting in the car, but you have the LiDAR and taking over the battery, so I think you have an extra battery, plus you have the gas consumption. I don't think these companies are revealing the cost it is to just run an autonomous car. I know it is expensive to do an autonomous car, especially when we do conversion. When you convert a non-autonomous to an autonomous car, I think it's very expensive. But mass scale, maybe it becomes cheaper. But right now, not just the computing cost, but even the heat, the overheating of the car itself is a big issue, because it's so much of processing happening in GPUs, and you have an air conditioning on top, which is just cooling the boot, not the driver, but not the people sitting in the car, but the computer sitting in the back is being cooled down because. So there's no single answer. You know, sometimes someone told me when I was about to present, I asked someone, what if someone asked me a very tough question, I don't have an answer? He said, oh, it's very easy. Give a bunch of other information, which is irrelevant information. That's what I tried, but anyway, picture now. Yes?
So on the same topic, rather than having each of the cars having logic to process, all this information, why can't we centralize it? Because let's say there's radar there, you can see a lot of the things only the car has to process, the remaining tree can centralize it, so that way you don't have to, everyone don't need to have high power GPU everywhere.
Multiple approaches are being tested as of today. For example, if you apply that question to a drone, there is an approach where each drone manages itself. If you have multiple drones flying, then you actually have each drone helping each other. Or you have a mother drone flying around and then managing all of the small drones. Or a cloud actually managing all the drones. All multiple types of approaches being tested. Some are being published, some papers are being published to just check which models are working fine. Some are not even published yet. So we don't know which one is the right thing. Centralization, one problem with the centralization, there are many problems with centralization. One problem I can see is what if there's no connectivity, cloud connectivity, and what happens to the car? Can you just randomly drive or so? So it's a difficult thing, and I don't know the answer to, but centralization sounds appealing, but it has some problem.
So how much did shopkeeper one lose on the £20 note? The fake £20 note?
Yeah, I'll tell you the answer. That's the question I had for you guys. Yeah, but whoever gives me the answer will be fantastic. I think Joe is going to give them a bottle of beer. Yes, sir. You had a question?
You spent 6 years at Apple. Can you explain why you left that?
Oh, God.
Because obviously you don't need to share it about it.
Yeah. I'll tell you the reason why I joined Apple and why I quit. Both were the same reasons. I sold my first startup and joined Apple, and I quit Apple to do my second startup. And both got acquired, thankfully, but that was the reason.
That's a very good PR answer.
Yeah. I didn't pay him, but yeah. Yes, sir. Yeah, in the back.
Oh, sorry. Okay. Compared to 2D image recognition, isn't it difficult to create point cloud training sets?
Point cloud training. Is it difficult to create? Oh, you mean any data set creation?
I mean, we can all take a series of two-dimensional images
Oh, it is. It is. Yeah, companies love it, and there is a good amount of business, especially for some of the low-cost countries trying to do good business out of it, annotating data sets. We ourselves do it. We actually send a couple of assignments to Poland. We have a company working for us in Poland. Also, we're looking for a company in India, which actually does annotation. Yeah, it's very expensive. Compared to 2D, 3D is even more expensive. I was told 2D takes, let's say, one simple complex image, it takes maybe 1 hour, but for a 3D image, it takes maybe 5 to 6 hours of annotations, careful annotation of the pixels. Because when you do a semantic segmentation, you actually have to identify which pixel belongs to which class. And then you do a border, and then you color all the pixels in the middle. It's expensive. It's a good thing and a bad thing. It's a good business too. I think if you want to start a company, it'll be a good idea, because there's a huge shortage of annotated data sets.
Have you tried?
Yes, sir.
Apart from star tracking, what kind of implementation can this 3D point cloud be used for?
Medical imaging, CT scans, for example. Medical imaging, when you do a CT scan, you can do that. So autonomous vehicles, which includes your cars and drones, CT scans, medical imaging, and then you also have the AR and VR, augmented reality and virtual reality, gaming. You can when you create games, I think you want models to run to find out, and especially you're doing the AR, augmented reality, where you're trying to look at the reality and also put some augmented stuff in it. You want image processing model to actually figure out what's happening inside. So these are the 3-4 areas. And it also goes into the brains of robots too, especially if you have a walking, rolling robots. I think they have a 3D image of the world view now, not 2D image anymore, because you actually have a richer representation if you take it 3D and not just 2D. So any robots is another thing too.
Two more questions.
Two more questions? Okay.
When you have, I guess, you had those matrix manipulations going on to get the results. What functions do you give to the next, or are there the derived functions from AI? Is that what it is? I'm trying to understand how you go from your left-hand matrices to the end.
Yeah. So what we do is, when we train a model, we take first an image where a human being has already drawn a line around borderlines around images or pictures, and we give that point cloud to the model, and then it does some computations, and at the end, it says, oh, there is a cat in it, but actually it's a dog in it. So we tell the model, no, that's not a cat, it's a dog. And the model does some internal computations, it's called backpropagation. It goes back and adjusts some things in it, and some things are called weights in this case. And then I give another image now, maybe a different cat or a different dog, and then that process goes on hundreds of thousands of times, millions of times actually. If you have a data set of 1,000 or 10,000 actually, or 1 million, you would run that 10 times or 20 times. So you're actually talking about 100 million times the model. It's like a human being. You make the human being sit there and give him a tight slap and say, okay, this is a cat, this is a cat, this is a cat, this is a cat. And I said, oh, I know, now that's a cat. Yeah, now I know. But the only difference between a human being and a model is that the model takes a lot more images to understand. Human being maybe takes, I think, only 1 or 2 attempts.
So taking it to the driverless car, I guess you tell it you shouldn't have killed that guy.
Yeah. So that's what's actually happening now. So they take videos of a driver driving on the street, and we take a video, and then you see how you're changing lanes and avoiding cars and avoiding pedestrians, and we bring that video and give it to a model. You say, okay, you know what, that's how you need to drive. Model says, okay, I'll try, and then you take the model and then start letting it drive, and it starts crashing, but you do only those things in virtual reality, so that every time it crashes, you say, oh, you know what, you're crashing, you're not really driving like that human guy, and that's how the whole
So you use simulations to train it.
Let's say simulations, yeah, let's say we can say that. Last question, I have 2 gentlemen raising your hands. Can I take Joe to both the questions? Yes, sir, let's go with you, and then we'll come to you in a minute.
Well, you spoke about poking the algo, or poking the... I just want to relate a situation. In Greenwich, there's a bus, self-driving bus going around, and there was a situation wherein a parent threw their kid in front of the bus to see if it stopped.
Okay.
It's real. it happened.
Wow, I want to find out
it
who
did
the
stop.
parent is.
It did stop.
Oh, it did stop. Okay, okay. Yeah, so it's working. It's working. Even though it's a bad way of testing, but
yeah,
it's working. Yeah. Okay, well, maybe I think we should find out who the parent is and let the kid grow. After he grows up, we should tell, this was who did it. Maybe he can do a reverse thing too. Yes, sir, you had a question. Last question.
Something about related to the models that you've actually discussed. Have you come across, so when you input a 3D point cloud, you're looking at X, Y, Z. But you can also get RGB values. If you get LiDAR data set, you have intensity values. You do a multi-spec LiDAR, you have a lot more data dimensionality.
Sure.
Have you come across any models that could actually process that complexity of dimensionality, and if there's any difference between just processing X, Y, Z?
The research is such in infancy. Right now, people are just trying to prove that point clouds, you can do processing of point clouds. So they're taking the most basic information, that's a grayscale picture. So you actually just only do X, Y, Z. But PointNet people, they actually tried X, Y, Z and RGB too. They have actually done that. I think they went to 6 dimensions and also went to 7 dimensions too. But any further dimensionality reduction, let's say they've taken 100 dimensions. I don't even know what the 100 dimensions could be. Let's say there's 100 dimensions, you can reduce the dimensions and process it. The dimensionality reduction as a technique itself has been proved multiple times, so we don't need to reprove that. Maybe I think when we put it together, it may become complex, but we don't know. But as AI scientists, what we are right now trying to prove is, can I do a point cloud and have a model which actually can do the processing within the time I want it to, let's say 20, 50 milliseconds, and also with tolerable computing power. Right now, even training plus even inference is happening on the cloud. We would want to reach a stage where I could do the inference on my cell phones. Eventually, there would be, I think, a time, maybe in a couple of years from now, your cell phones would be able to do the semantic segmentation on your cell phones, but right now, I don't think it's actually happening. There are some AR, VR applications available already, like IKEA app, I think you want to purchase a chair, you show it to your kitchen and then pick it and it will actually show you. There's a little bit of AR, VR going on, but that's a very, very small model sitting on your cell phone, which actually has a GPU too. But yeah, the answer is no, we have not seen the experiments yet on that, multi-dimensions, yeah. Okay, thank you guys, thank you very much, I appreciate it.
Please come back, please don't go.